Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we will present about mini project power system control. This is all my team. My name is Muhammad Faisal Ibn Muhammad Munir, Muhammad Nur Iman bin Taini, Muhammad Al-Razan Syah bin Ahmad Yaakob, Muhammad Ikmal Amrullah bin Fiji. Okay, in this topic, we have choose lower frequency control in PID controller gain. Now, I will go through about load frequency control or LFC will be present detail by my friend Muhammad Nur Iman. Okay, I pass to him. Please.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iman bin Zaini. I will present about load frequency control. The following basic requirements are to be fulfilled for successful operation of the system. First, the generation must be adequate to meet all the load demand. Second, the system frequency must be maintained within narrow and rigid limits. Third, the system voltage profile must be maintained within reasonable limits. And fourth, in case of interconnected operation, the tier line power flow must be maintained at the specific value. When real power balance between generation and demand is achieved, the frequency specification is automatically certified. Similarly, with a balance between reactive power generation and demand, voltage profile is also maintained within the prescribed limits. Under steady state condition, the total real power generation in the system equal to the total of megawatt demand plus real power losses. Any difference is immediately indicated by a change in speed of or frequency. Generators are fitted with speed governors which will have varying characteristics like different sensitivities, that band response times, and groups. They adjust the input to match the demand within their limits. Any change in local demand within permissible limits is absorbed by generator in the system in a random fashion. Next. The control of generation in this manner is termed load frequency control. Should the generation be not adequate to balance the load demand, it is imperative that one of the following alternatives be considered for keeping the system in operating condition. First, starting fast peaking unit. Second, load shedding for unimportant loads. And third, generation rescheduling. It is apparent from the above that since the voltage specifications are not stringent, load frequency control is by far the most important in power system control. Next. Okay, this is the figure for the block schematic for load frequency control. Okay, I think that's all for me. I will pass to my friend back. Okay, thank you.
Okay, thank you, Mr. Nur Iman. Okay, now I will revise back what Mr. Iman talked about. Okay, in this topic, load frequency control that we know is want to generate most adequate to meet all the load demand. This show that when we control any controller, the load frequency control is the most important part to control the peaking unit, the shading loads, and the generation when reschedule the program. Okay, now we will go more to PID controller. I will pass this more to Mr. Ikman. Please.
Hello, my name is Muhammad Ikmal Amrullah, and good evening to everyone. Do you can hear me?
Yeah, please.
Okay.
Yes.
First, PID controller. PID is an acronym for the mathematical term proportional, integral, and derivative. Proportional means a constant multiple. A number is said to be proportional to another if there exists a constant n such that y equal nx. This n can be positive or negative, greater or less than 1. To make the formula more accurate by PID controller standard, proportion is given by Kp and the x term is the control loop error. Derivative is the rate of change during a given interval, interpreted by a PID controller. Next. Okay, as you can see, there is a graph about proportion spot fixer. Uh, K equal to 5, K equal to 2, and K equal to 1. When you can see K equal to 5, there was a too much gain, cost overshoot. Larger proportional gain or error increase output from the proportional factor. Caution setting proportional gain too high can cause a controller to repeatedly overshoot its set point. Okay, all three of these PID controller components create output based on measure error of the process being regulated. If a control loop functions properly, any change in error caused by set point change or process disturbance are quickly eliminated by the combination of three factors P, I, and D. Let us now analyze how each contribute to performance. Proportional factor. The proportional factor is easiest to understand. The output of the proportional factor is the product of gain and measure error E. Hence, larger proportional gain or error make the great output from the proportional factor. Setting the proportional gain too high cause a controller to repeatedly overshoot to set point, leading to oscillation. The downside to a proportional only loop is that when error becomes too small, loop output becomes negligible. Therefore, even the proportional loop reach steady state, there is still error. The larger the proportional gain, the smaller the steady state error. But the larger the proportional gain, the more likely the loop is to more unstable. This dilemma leads to inevitable steady state error called offsets. Next is integral factor. Next slide. Okay, there was a graph for integral factor. The integral factor is like a basket that store all measure error. When the integral is functioning correctly, the basket is always nearly empty. Think of the integral factor as a basket in which the loop store all measure error. Remember the error can be positive or negative. So sometimes error fill the basket when positive error is added to positive error or negative error is added to negative. And sometimes it empty the basket as when positive error is added to negative or vice versa. When the integral factor function properly in the control loop, the basket is nearly empty even when error is so small that the proportional factor is no longer effective. The integral is still hard at work, collecting error until it is large enough to matter. As part of the integral function is to eliminate steady state offset. Lastly, derivative factor. The derivative factor is the least understood that use of the three factors. It account for an correct present error versus error at the last check. Next slide. The derivative factor is the least understood and used of the three factors. In fact, a majority of PID loops in the real world are really just PI loop. That does not negate the fact that there are content applications in which the derivative plays as an important role. The proportional corrects instance of error, the integral correct accumulation of error, and the derivative correct present error versus error and the last time it was checked. Okay, next I will explain about LFC in PID controller. As long constantly varies, the power system operating conditions are always changing and hence precise manual control of the balance would be impossible. PID control offers the simplest and yet most efficient solution to many real-world control problems. Three-term functionality of controller cover treatment of both transient and steady-state response. Conventionally, PID controller was widely employed for proper tuning of gain in LFC and LVR in power system. The PID controller is simple for implementation but generally give large derivation. The conventional controller used today are fixed gain controller and are insufficient because of change in operating point during a daily cycle. As the operating point of a power system changes continually, a fixed gain controller may no longer be suitable in all operation conditions. The speed governor system should be operated within the restricted control range of feedback gains due to the instability. Moreover, in the deregulated environments, frequent on-off control of large capacity unit may bring out large amount of power disturbance. I think that's all for me. Now I pass to Mr. Faris.
Okay, thank you, Mr. Ikmal. Okay, what we know that uh, first Mr. Nur Iman tell about LFC. Now Mr. Ikmal tell about PID controller. Okay, in the summary, a PID controller is what we learn is proportional integral derivative controller. It can keep an automated process like temperature, pressure, flow constant for the automatically process controller. PID is used a control loop feedback to monitor where the output should. Now we go to why LVC in PID controller. Okay, the aim of LVC is to maintain a real power balance for the control. So whenever the real power demand change, the frequency change occur, so that the LFC will control the frequency to balance our control system. Okay, now we will go to the problem and solution in MATLAB. Okay, now the problem and solution in MATLAB, I will talk more. Okay. Okay, now the question is, we know that the gain is for turbine, generator, amplifier, exciter is for LFC side. Okay, the generator sensor initial regulation is for PID and LFC also. Okay, we know that in this question, we will know more about this all talk about the gain and synchronize of the motor. Okay, now we set the PID controller is tuned by KP1, KI 0.25 and KD is 0.3. Okay, I'm sorry now because I can't open the MATLAB because my laptop is not too good now. Okay, and then here I want to talk about is my screenshot of simulating. Okay, in the upper side is for LFC and the lower side is for PID. Okay, in this we know that our things is this is gain, this is transfer function, our scope, our I don't know what this thing. This is add minus, gain, this marks, and then scope also for PID and PID controller. Now we will sketch all our MATLAB in this line using this diagram to create a PID controller in LFC side. Okay, and then we will set all our things in KT, KA, KE for in the transfer function in the nums and the numerator and the denominator. Okay, after this we set all and we will set the KP, KI and KT in PID controller. Okay, after that we will run our simulation with using 15 time cycle. Okay, for that thing, the result is for frequency deviation setup response. The result is a bit overshoot, but it's lower than 0.05. It's good for the frequency deviation setup, and then we will go maintaining in the line of 0. For voltage step response, we know that the thing is when the start is also overshoot in the arc of 1.6, but after 5 until 10 cycle of time is more mentally on one, so the gain is stability. Okay, that's all. Now we will go through for the conclusion and how the LFC and PID will work. I will pass this more to Mr. Norafizan. Okay, please.
Okay, a very good evening to all my friend and my beloved teacher. Today I'm gonna explain about the conclusion. For conclusion, the LFC or the low frequency characteristic of a single area power system with non-reheated and reheated turbines have been deliberated. The proposed method is flexible and gives satisfactory performance in nominal as well as the per tube case. The proposed PID controller with a new control structure and a single tuning parameter beta gave better performance than TAN's controller. PID tuning technique for LFC has been done. Also, I've attempted to include most of the advanced in the PID design. The primary challenges in FC is to develop a highly robust PID controller that maintain frequency deviation steadily in specified limit even in the presence of non-linearities. Give GDB or like governor deadband and generation rate constraint. Physical constraint and uncertain environment and validate it on a appropriate hardware setup. Controllers, how they work. Actually, this table show that the Ziegler or Nicholas method, which is we can see there is a three type of control type. For the first one is P on D, second PI, the third is PID, and we can see the value for KP, K1, and KZ. Okay. How a PID controller works is a pretty easy concept to understand. The PID controller look at the current value of an error E, the integral of the error over time interval integration, and the rate of change of the error to determine how much of a correction to apply. The controller continues to apply the correction until change is seen on the feedback. Depending on the error calculation update rate, which in turn may depend on how often the loop feedback is read. The corrective action can be adjusted at a fast rate. For instance, the analog feedback on some variable frequency drive is updated every 10 milliseconds. The job of a PID controller is to force feedback to match a set point. Sometimes, error between feedback and set point is caused by a set point change. But in most applications, the set, can you move to the next slide? The set point is not adjusted much. More often, error in a loop is caused by disturbance in measure feedback. Okay, I think that's all for me. I will pass back to my leader. Thank
Okay,
you.
thank you, Mr. Norafizan. Okay, now I will more conclude about LFC and PID. Okay, and we know that LFC, the most part that more important is GDB and GRC, that governor that band and generation rate of constraint. But in PID, we have control the PI. I'm sorry, wait, I forgot. Okay, in the PID controller, we will set for KP, KI, and KD for the set of the what I will call it the limit of what we can set to control our system. Okay, so when we gain about LFC and PID control, that will give more accurate data that we get after we changing the frequency for our control system. That's all from our teams. I think That's all. Thank you very much.